Facial expression classification. The introduction. We choose to address the problem of facial expression/mood classification. The ability to read and understand expressions is something that comes naturally to humans, acting as an extra dimension of everyday communication that adds context and emotion to the words someone says. So, in the pursuit of human acting agents, this dimension of communication must be taken into account. We believe that the main area in which this type of model could make the most impact is in natural communication with software interfaces such as voice assistants, which must interpret natural human speech and its intent as accurately as possible. By adding the context provided by facial expressions, these agents can better interpret the subtleties of human communication. Contributions. Evan White, the team leader, directed and supervised the group, created a working prototype, made necessary changes to improve validation accuracy, and collaborated on the project proposal, presentation, and final report. Like the rest of the team members, William Lindner, Edward Schulze, both assisted in researching and testing and collaborating on the project proposal, presentation, and final report.
For our dataset, we use the FIR 2013 dataset, which has just under 36,000 entries. It consists of 48 by 48 pixel grayscale facial images with a label for the facial expression displayed. We didn't end up using the original labels from this dataset. Instead, we used the labels from the FIR Plus dataset created by Microsoft. FIR Plus uses voting from a group of 10 people to determine the label rather than just using a single vote like the original dataset. So there's 10 labels for each image, each corresponding to the number of votes for each expression for a given image. And the possible expressions are neutral, happiness, surprise, sadness, anger, disgust, fear, contempt, as well as unknown and not found. So this FIR Plus dataset seeks to provide better ground truth for the model to train upon. And with the votes, we decided the label for each image using just a simple majority vote method. There's other methods you can use. We'll talk about that later in the presentation. But for the purposes of this model, we just went with the simple majority vote. And we split the data 80-20 into training and validation. And so here's some examples of the FIR 2013 labels versus the FIR Plus, so you can get an idea of what's meant by better ground truth. So the FIR labels are on top, and then the revised FIR Plus labels are on the bottom. And so if you look through these images, you can see that some of the original labels from the FIR 2013 dataset are a little questionable, and the FIR Plus one just gives a stronger foundation for the model to make its predictions on. So for the model, we used a convolutional neural network with 4 convolutional layers and 2 fully connected dense layers. We also made use of methods such as batch normalization, max pooling, ReLU activation, dropout, and softmax activation to improve the model performance, increase learning rate, and to avoid overfitting. And we trained the model for a maximum of 100 epochs, saving the weights only from the best performing epoch with the highest accuracy and lowest loss. This is a screenshot of our code showing the model architecture. For the purposes of the presentation, I won't go too into detail, but you can see this is the 4 convolutional layers. And you can feel free to pause this if you want to look a little deeper into it. And then we also have the 2 dense layers, followed by the final dense layer, which splits it out into the 10 different classes using a softmax activation. And so before we talk about the results of the model, I think it's good to give a little context and look at some benchmarks. So this is the performance of 8 different commercially available facial affectation classifiers. And then it also shows the control group, which is human observers, which surprisingly enough, only score an accuracy near 75%. And so Our model, we had a validation accuracy of 72.9% and a validation loss of 1.7317%. And if you look at that compared to the previous chart I just showed, it seems like our model is doing, really well. That's higher than all of the commercially available models, but you have to remember that this number that we're looking at here is just the validation accuracy. So it's looking at data that's from the data set, and therefore, even though it's split off from the training data, it's going to share some similarities with it. And the figures that are presented in the chart shown before, those are from real world data. So that's why our model might look like it's a lot closer based on these numbers, but in reality, it's probably not. I find it hard to believe that we outperformed commercially available products. We probably didn't. If they put ours under the same rigorous testing that they put those ones under, I'm sure we'd fall a little bit short. And so going on from the results, we see some examples of images that we fed through our model. And these are their predictions. Obviously, the first one is angry. I think we can all agree that that's correct. Same with the second, happiness, and then the third, surprise. And then we also have a video example. So this is from a live webcam feed. All right, and just a quick note on the facial capturing from the video. This was not a part of our model. Actually, the part where it finds the face from the video, that's not part of our model. This was implemented using the OpenCV Python library with the har cascade frontal face default cascade classifier, which was created by the University of Augsburg professor Rainer Lindner. I just wanted to make a note of that. That was not part of our model. So we went about validation by checking the model's performance on classifying the validation data, which showed the accuracy figures from before. Also, after each iteration on the model's design, we didn't treat the validation accuracy as our only source of truth. We also performed some sanity testing using user-provided images as well as the live video feed that I showed before, just to make sure that we're not just seeing accuracy increases in the validation set that don't translate over to the test data, the real-world examples. So this additional testing allowed us to determine whether the model's performance on the data set also extended to the real-world examples. And there were some instances where the validation accuracy would increase, but the real-world performance would worsen. So, we would see the accuracy maybe shoot up near 75%, but then we would go and test it on the webcam or on the command line by providing it image URLs, and it would be making some very weird classifications. So that just goes to show that you can't treat the validation accuracy as ground truth. You have to also do your own testing on real-world data. And so now to discuss some of the shortcomings in the model. So one big one that definitely impaired us a little bit during the creation of the model was very long training times, especially because we don't have a GPU. That would obviously cut down the training time significantly. And hey, maybe that's a suggestion for Brockport. Provide some computing resources like that. I don't know. But yeah, obviously that could have been improved with more computing power. Another thing is that some expressions are recognized with a much higher accuracy than others. So for example, happiness, anger, surprise, and neutral are almost always recognized. Those were the ones shown in the video example. The model does great on those. However, fear, disgust, sadness, and contempt are very often miscategorized as one of the previously mentioned examples in that first group that it does really well on. And so my theory as to why is that the latter group of expressions are in general much more subtle. And also some of them are very similar to the emotions in the former group. For example, disgust is very facially similar to anger. It involves a furrowing of the brow, scrunching of the face. So for the model to pick up on that, it would probably have to be one, a lot more complex, and two, the data set should consist of larger images so that the model can pick up on those more minute facial details. 48 by 48 images don't necessarily give that level of detail to the images. And to continue on this, the model only really performs at its best on front-facing images in good lighting. So this could obviously be improved by expanding the data set to include facial images in poor lighting, as well as facial images from different angles. And then one last shortcoming that we realized was choosing labels by majority vote does leave out the significance of the other votes. And so this can be improved in many ways, two of which are multi-label classification, and then the one that has been shown to perform the best is probabilistic label selection during training. So while the model is going through the training, when a certain image is being passed through the model, at each step or at each iteration, it probabilistically chooses which label using the probabilities of the number of votes per emotion. It chooses it based on that. And so if you run it enough epochs, that will begin to approximate the true probability distribution of the labels. And so that performs best.
We use Discord as our main source of communication throughout the course of this project. We also use Trello to assign tasks. Trello was really helpful because we were able to view what tasks Evan had assigned to us, and then we could move the tasks through different categories as we worked on them. Also, if we needed to, we could comment responses or questions on each task. This project was a great insight into how a very human task can be completed by a computer and what goes into completing such a task. This technology can be used in many different fields to help provide more context to human communication for software interfaces. And lastly, it was fun to make. It is interesting to take something so subjective and attempt to capture it in an objective mathematical way. Here are references that we used and found interesting. And lastly, our appendix with a link to our code, our data sets, and a resource we used to build the model.